Let's go to the next lecture. I introduce Professor, so everybody knows, Professor William Meeks, who is going to talk about the local and global geometry of embedded, minimal, and CMC surface in three manifolds.
Okay, so I'm going to talk mostly about work that I've done in the last couple of years, and it's been a very exciting last couple of years. Probably should say the same thing Harold mentioned to Marcos. I don't think Marcos is here, I don't see him, but that I hope he continues doing good work. Harold and I continue forging ahead, even though we're over 60. So anyway, I would just want to mention there are a couple, sort of three things I think that have been very important that have happened in the last couple of years that sort of influence the subject, and also sort of probably useful tools and so forth for the future. And I'll just mention those as introduction of KDB theory to understand minimal surfaces in R3. Another thing I think I like quite a bit is this idea of dynamics theorem, looking at collections of surfaces and somehow operators on the spaces of surfaces, and looking at what are called dynamics. That plays a very important role also in what I'm going to talk about today. Let's see, what else? Removable singularity theorems is certainly the way of the future. We really need to understand, to progress in this subject, we need to understand singularities or the non-existence of singularities. So those are really sort of food for thought. Okay, so let me start at the very beginning. Minimal surfaces, so we have, everyone's pretty familiar with the definition of that. I'd say I probably want to focus, I was going to give you an example, sort of properties, the equivalent properties. This property that the coordinate functions are harmonic, at least for me that seems to be one of the more useful properties, and that the Gauss map is a meromorphic function on a minimal surface. So I'm thinking orientable in this case. Okay, so we have the definition of minimal surface. I'm just going to explain by way of a picture what this is about. We have a conformal Gauss map. So that sort of the picture is this. We have this meromorphic Gauss map. So we think of it like a little soap film in space of the topology of the disk. And then we can always parameterize it conformally by the unit disk in the plane. So here, imagine this is coordinatizing that sort of soap film over here. We have, at each point, we have the unit normal. We can translate that to the sphere. It turns out that's also a conformal map where the derivative is not zero. And we can take stereographic projection from the North Pole, and we get a point in the extended complex plane. And so altogether, all these maps are conformal, so therefore the Gauss map to the extended complex plane can be thought of as a meromorphic function on the underlying Riemann surface, or the surface that's minimal in R3. Okay, so I say that's also important in my talk. All right, so one of the things you get out of these meromorphic properties, like the coordinate functions are harmonic, the Gauss map is meromorphic, is we can represent all minimal surfaces in R3, sort of by analytic formulas. So we have, for example, we have the sort of Gauss map, which is a meromorphic function. We have what's called the height differential. It's not a closed, it's written as if it's closed, but it's not really the differential of any function. But anyway, it's the sort of this complexification of the differential of the third coordinate function. And we have a way of recovering the surface up to translation by integrating this holomorphic data. So this is really like a holomorphic function times a or meromorphic function times a holomorphic differential. And we have these sort of three forms you can think of kind of written out this way. If I integrate those, I get three complex numbers, and I take the real part of those three complex numbers, then I want that to be well-defined. In general, these three complex numbers are not well-defined. Only the real parts are well-defined. And then I can recover the function in an analytic way. All right, so that's called the Weierstrass representation. And let me just point out a useful application of it is to create minimal surfaces with certain properties. So of course you have to try to create the right functions and everything to make these properties actually occur. So this kind of thing, one application that I think is fairly important is this solution of the smooth, proper Calabi-Yau problem for arbitrary topology. So the smooth refers to bounded smooth domains in R3. So take your favorite bounded smooth domain in R3. Right, we probably could relax. We can relax some of these conditions, but basically, bounded and smooth. You take any open surface. The surface could be non-orientable. It could have an uncountable number of ends. Maybe all the ends have infinite genus. Some of them do, some of them don't. It can be very complicated, generally, these surfaces. And basically assume it's connected. Probably one property of what. Then you take this surface, then I can make a proper immersion of that surface into that smooth domain I picked out in such a way it's complete. So I can put that surface in a proper way. So every compact subdomain of D intersects the surface in a finite area, for example. And yet it sort of wanders, as you go to infinity on the surface, you wander out to the boundary of this bounded set. Okay? And in fact, we actually got a lot of control on such a mapping. In fact, we can do this so that the limit sets of different ends, if you take a given n, there's a notion of its limit set. It's defined in terms of exhaustions of the end, but basically the ends limit to some compact subset of the boundary of the domain. And it turns out if you pick different ends, then these domains are disjoint. So ends stay a positive distance from each other. Take two ends, they sort of stay away from each other. And that turns out to be important, that last property, because we would like to remove the proper minimal immersion, complete proper minimal immersion, to complete proper minimal embeddings. And that's maybe kind of hard to believe that you could do that, but that's what we want to do. So that's called the sort of question is related to what's called the embedded Calabi-Yau problem. So the question, if you want to think of, you could ask here, simple question would be, does there exist an open surface with a complete injective immersion of it into like a ball in space? That would be the simplest way to propose this. But we actually think that you can do much better, and you can even understand this problem in a much deeper way. This is, of course, just a talk, and I'm just going to illustrate sort of one aspect of what we believe. There's this particular domain we define. It's got infinite genus. It's not smooth. It's not smooth except at one point. And the claim is that this domain is a universal domain for the bounded Calabi-Yau problem. Okay, it's universal in what sense? Well, maybe I should tell a little background on this. If you try to have if you take an annular end of a bounded minimal surface that's complete end, it can never be embedded. That's a recent result of Colding-Minicozzi, and there's the guy over there, one of the people. So if you try to do this with a surface that has an annular end, you can't properly embed it into a bounded domain. The annulus is always asymptotic to sort of like a helicoid or a catenoid or a plane, something that's like sort of a helicoid. That's, again, related to the later thing in my talk. So there's some topological obstructions in general to putting a surface into a bounded domain in an embedded complete way. So for example, you can prove that any end of the surface that can be represented by a subdomain, a proper subdomain with compact boundary, if it has a countable number of ends, it also is not allowed. Okay? And there's some hope in understanding exactly what's happening in this problem. Anyway, the conjecture says that you take this particular domain and you look at any open surface. It can be non-orientable. It can have an uncountable number of non-orientable ends. It can be very complicated. But as long as each end has infinite genus, then it will properly embed in this particular bounded domain. Now, if you want to do it in a ball, you can't do it because, first of all, if you did it in a ball is simply connected. It would have to separate the ball, and it would have to be orientable. So There's related conjectures, but I kind of like this one. It sort of summarizes that exactly when do you have complete bounded immersions, injective immersions. If they exist, the claim is they exist in a very beautiful way. They occur as proper embeddings in a particular domain. So that's, again, it's related to, I think it's a good chance of proving both. So there's an existence and a non-existence result. This is more what the existence result is. Okay, so now I'm going to talk about some particular results. Here we have a picture of the helicoid, 2 pictures of it. It has this very simple Weierstrass representation. The surface is formally complex plane. You take the height differential, dh, just to be dz in the complex plane, and you take the Gauss map to be e to the iz. You plug that into the Weierstrass formula, and you create the helicoid. Okay? And you can do a similar thing to make a catenoid. So we take the complex plane, puncture it at the origin, take this particular meromorphic or holomorphic form on it, and you take this very simple Gauss map. Then it turns out you get the catenoid. And I want to talk a little bit about uniqueness properties of these surfaces. I guess the first thing was proven by Lopez-Ross. They proved that if you take a planar domain in R3 with finite total curvature that's complete and embedded, then, and finite total curvature, then it's the catenoid. Okay, that's Lopez-Ross. Pascal Colin then later on came along, and he proved that if you had a surface with finite topology and at least 2 ends, a minimal surface that's proper in R3, then it always has finite total curvature. And then more recently, Kolde-Minekosi proved that whenever you have a complete injectively immersed surface of finite topology in R3, then it's always, if it's complete and injectively mapped in, then in fact it's proper. And so it has finite total curvature by Colin, and if we had a genus assumption, we'd have a genus 0 assumption, then we'd know it was a catenoid. So this gives, in the end, a uniqueness theorem for annuli, or for planar domains with a finite number of ends bigger than 1. Okay? All right. We also have some kind of similar results about the helicoid. So it's the unique, simply connected, complete, non-flat, embedded minimal surface, because you have the plane. So we're talking simply connected, sort of the crucial thing here. And under the hypothesis of proper, Harold Rosenberg and I proved this result using some results of Kolde-Minekosi. And then, as I said before, the assumption of properness is not necessary because Kolde-Minekosi proved that all complete injective examples like this are always proper. So you have that. It's very important to know properness to do barrier constructions and try to analyze the geometry of a surface. If it's not proper, it's very, very hard to deal with understanding it. Okay, so that's what we have. There we go. So those are the ones sort of finite topology genus 0 examples. Then we have this beautiful examples that Riemann found about 1860. I put down here. This is not exactly when it was published. I mean, he had some health problems and different things. But anyway, in about 1860, he discovered generalization of the helicoid and catenoid. The helicoid and catenoid have the property that horizontal planes intersect in circles, like the catenoid, or in straight lines, like the helicoid. So what he did is he kind of generalized that. Suppose there exist examples which are somehow in between. Most planes intersect in circles, round circles, and some planes intersect in straight lines. So he wrote these examples down in terms of the Weierstrass P function on rectangular elliptic curves. So the Gauss map was the Weierstrass P function, for example, or some constant times it. And the height differential was just dz. Of course, this isn't a torus. This is a covering space of a torus. So you lift this information to a cylindrical covering of that torus. You puncture at points where the data goes to infinity, and you make this particular example. Well, not just this example. You make a whole one-parameter family of these examples. So this is just trying to understand what is the topology of these examples. So at each level, each height, we have either a straight line or a round circle. And it turns out you can actually parameterize these surfaces conformally by an infinite cylinder of a particular radius, and such that the height function is just the height function of the cylinder. So each level in the cylinder, I see sort of a curve. Some places I have a straight line, like right here or right here. And so a straight line is nothing more than removing a point from a circle. So we see that we have this very nice picture of what the Riemann surface is. And you can see it now has genus 0 because it's a subdomain of a cylinder. And a cylinder is just an annulus, and the annulus is, it certainly has genus 0. Okay, so this picture is it's sort of hard to do with computer graphics. So this gives more of a flavor of what it looks like. What does Riemann look like? It looks like a stack of planes at integer heights. And then you kind of join, you sort of have a staircase of tubes. You put a little cylinder between those planes, and you do it in a diagonal way. So these are periodic surfaces that somehow have a under translation, they go off like that. Okay, so I'm going to talk a little bit more about these. So notice that, remember they had this picture of the cylinder. The height of the ends are the heights where you have the plane, so these planar ends in the previous picture, but they're the heights where you have these lines on the surface. You can see the lines, and those are the points you're going to remove from the cylinder. Now, a cylinder, if you compactify it, it's an infinite cylinder. You compactify it by adding the top end and the bottom end. We have nothing more than the two-sphere. So again, I'm trying to understand what's the topology of the surface, and what's the, what does it look like? So another way to understand it, it looks, it's conformally, you take the two-sphere, you remove the north and south pole, they're going to be limit ends, and you take a sequence of points that converge to the north and south pole. Okay? And that's the topology of Riemann. It's very easy to see from this picture. It's the surface of genus 0 with two limit ends. For genus 0 surfaces, that's a way of classifying them. So this is a non-compact surface, but it's fairly simple. It only has two limit ends, has infinite topology. All right, so what do we know about Riemann? Well, it was discovered by him. He had a one-parameter family of examples. Horizontal planes intersect in circles and lines. And then we have, again, one of these uniqueness results. It says that, that if you look in the category of properly embedded minimal surfaces in R3 with genus 0, we'd like to remove the word proper and say complete, but right now we still have the word proper there, and you have infinite topology, then you must be one of Riemann's minimal examples. Okay? So that's a fairly recent result. I'm not going to really say too much about it. I can say somehow a KdV equation comes up. The Gauss map, somehow, some rational combination of the Gauss map and its derivative satisfies the, when you unravel the cylinder and go up the complex plane, satisfies the holomorphic KdV equations. Anyway, all right, so I'm just thinking about basic properties here. What happens, it's always interesting, what happens as the parameter on the Riemann examples goes to the limits? Like, what happens when you go to the boundary of the moduli space of these examples? Well, in one direction you go to catenoids, in the other direction you go to helicoids. And this picture actually came up, we studied this problem, I don't know, 13 or 14 years ago. We proved something. We used very strongly what's called a parking garage structure. We proved this theorem originally for periodic genus 0 surfaces with infinite topology. And it was very important in that proof that there was somehow an asymptotic behavior as something goes, one of the parameters goes in a certain direction. So that's this sort of picture. If you go toward the helicoidal limit, you really get two helicoids that somehow glue together. And in the limit, they sort of, you get a foliation of R3, and you don't converge smoothly along two straight lines. And along those straight lines, it starts looking like a helicoid. Okay? So that plays an important role, actually, in somehow the proof itself, is that sort of limiting behavior. Okay, so anyway, so in the end, we have a nice classification theorem, at least for proper. We have the moduli space of genus 0 surface that may be thought of as a compact interval. At one end points the catenoid, one end points the helicoid, and then we have the Riemann examples in between. So that's a nice way to think of the moduli space of the examples. And I should say, at least yesterday, I spent some time trying to get rid of the properness hypothesis. I think there's a good chance. I was very positive at the end of the day, but I couldn't Couldn't do it. One would like to remove properness. In other words, complete and embedded implies proper if you have finite genus. And we know it in lots of cases, and I think I finally found probably the right way to do that. Okay, so now I want to go away from minimal surfaces to, again, a very classical situation in R3 of constant mean curvature surfaces. Of course, our favorite example would be the cylinder, or a sphere. But somehow there's a sort of a way of getting between the cylinder and the sphere, just like we got from the catenoid to the helicoid. And that way of getting from the sphere to the cylinder is via these periodic surfaces of Delaunay of revolution. And so what do we have? We have, say, we're looking at h equal to 1. We have sphere of radius 1. We have the cylinder of radius 1/2. And Delaunay, back in 1845, he classified all the surfaces of revolution, and basically they form a path between the cylinder and a chain of spheres. So there's something called neck size, see the neck here? If you let that neck size vary, if you open it all the way up, you get a cylinder. If you pinch it all the way down, you get a chain of spheres of radius 1 centered along an axis, a straight line. So that's what happens. Somehow you convert to the sphere or the cylinder. Okay, and again, we'd like to understand these surfaces just from a theoretical point of view. What are the annuli, for example, of constant mean curvature in R3? Not necessarily minimal. Okay, so a little bit more examples. Here's another Delaunay surface. It's a little more pinched, maybe a little less pinched than the one on the previous page. And it turns out that these are, just like the catenoid and planes or helicoids are sort of tell us the asymptotic behavior of minimal surfaces. I didn't talk about that before, but anyway they do. In the same way, somehow the Delaunay surfaces tell us what's happening on the asymptotic behavior of finite topology surfaces. So here's an example called a trinoid. I'll just put out the whole thing. So a trinoid, here we have a trinoid with somehow 3 annular ends. So this is a planar domain. It's a 2-sphere with 3 points removed from it. And I want to drag those points to infinity, and I do that by attaching essentially a Delaunay surface here. Maybe a Delaunay surface there and a Delaunay surface going over there. So I'm very quickly asymptotic to 3 Delaunay surfaces. In fact, exponentially quickly I'm asymptotic to fixed ends of Delaunay surfaces. Okay, so they're the model. They're our model for the asymptotic behavior of annular ends. Okay? So let me tell you a little bit about the, should point it this way. Okay, so I'm going to tell you a little bit about the history of these problems I'm going to talk about. So I'm interested primarily in H surfaces. H here, we've already talked about minimal. I'm thinking about H positive. So this means H surface means constant mean curvature H. So we have Delaunay, we have the sphere, we have the cylinder. What can we say about properly embedded? We have the trinoid. What can you say about properly embedded H surfaces in R3? Well, you can actually say quite a bit these days. So we had, of course, the classic result of Hoff, and he probably did it a little earlier than that. But if you even have an immersed sphere in R3 with constant mean curvature, it's round. Okay? But we're focusing on embedded, and now I'm thinking embedded and compact. Then Alexandrov proved that you're also a round sphere. You don't have any soap bubbles, which are tori, for example. So compact, constant mean curvature, embedded, then you're the round sphere. In fact, he also proved something a little more general. Then we have a big sort of jump in years. The subject sort of started up again, in my point of view, back, maybe, this is actually, it was published. It was a few years earlier I was doing this work. So I found out, I asked this sort of question, can you put a plane in R3 with non-zero constant mean curvature? Well, if I say proper, notice the word proper here, I proved you couldn't do that. Plane, constant mean curvature in R3, we now understand it's a plane or a helicoid. It can't have non-zero constant mean curvature. So there's a story coming up here. Okay, so more or less, right after I proved this result, Nick Korvar and Rob Kussner and Bruce Solomon, they sort of used some of the things I did, and they developed a few more techniques, and they proved that the Delaunay surfaces are the model surfaces for annular ends of constant mean curvature under the assumption you're properly embedded in space. Okay? In particular, kind of like we have the uniqueness of the catenoid, you have the uniqueness of annuli with non-zero constant mean curvature. They are, again, Delaunay surfaces if they have two ends. So if you take a torus minus 2 points, you can't put that in R3 properly with constant mean curvature because it has two ends. It would have to be a Delaunay surface. So again, we get some nice topological obstructions here, just like we had in that paper. OK, so I'd say pretty much this year, we've been working on this for a couple of years. So Giuseppe Tignaglia and I have been doing a number of different things, some of which I'm going to talk about now. But one consequence of those results is if you have a surface in R3 that's complete, embedded, H surface, and you have finite topology, then you are always properly embedded. This is kind of like Colding-Minicozzi for minimal. So this is the result I mentioned before we talked about in the minimal case. So we managed to improve or prove something different. It's somewhat similar techniques. We analyze the same kind of problem for non-zero constant mean curvature surfaces. All right. So I'm just going to talk a little bit. Oh, yeah. So again, one of the consequences of this is if you take a finite topology, complete, embedded constant mean curvature surface in R3, its ends are asymptotic to Delaunay ends. So here's some kind of interesting pictures. Those ends can actually have a cylindrical end and non-cylindrical ends. I mean, you can have these kind of interesting combinations of pictures. And again, part of the reason I did this was actually done in a laboratory at UMass a few years ago not by me. But anyway, so it's just one interesting examples. You can add more ends, and you can have cylinders. It just kind of illustrate what happens. And we know that this is what happens in general. You make these examples. This is what you see when you produce them, and that's what always happens. So we're nice to have a little theory. OK. So let me explain a little bit about my work with Giuseppe. The first thing is a curvature estimate for H disks. So H disk means I'm assuming H is non-zero, in this case, constant mean curvature 1. I'm looking for a compact embedded disks in R3 with constant mean curvature 1. What can you say about them? Well, the first thing you can say is they sort of behave like stable constant mean curvature surfaces. So at least in a certain kind of sense. So the first result is that if you go away from the boundary any distance at all, intrinsically, you have a curvature estimate, a universal curvature estimate. And if you don't like constant mean curvature 1 or 1/2, you can scale all these quantities. So you have to think about scaling things. But anyway, I just fixed constant mean curvature 1. Anyway, you get a bound on the norm of the second fundamental form away from the boundary, a universal estimate. OK, and how is this proved? Well, there's a famous one-sided curvature estimate for minimal disks by Colding-Minicozzi. And we found a very, very nice way of generalizing that without doing all the estimates all over again. So we have there's some theory. There's a lot of theory that's been done in the last few years. So basically, using that theory, you can prove similar kind of one-sided curvature estimates, at least in homogeneous 3 manifolds, like R3. R3 is an example. OK, so we have such things like that. So that's one thing. It helps you get what are called weak chord arc properties, a relationship between intrinsic and extrinsic distances. This is the crucial kind of arguments here that are used by Colding-Minicozzi to prove properness in the minimal case. The arguments here go a little bit more along the lines of something that Harold Rosenberg and I sort of generalized some aspects of their proofs. And the actual proof here is a little more along the lines of my paper with Harold. Partly just I'm more familiar with those arguments. But anyway. So what do? The weak chord arc estimates reduced down to a particular case. So you can think of a disk, constant mean curvature 1, on the boundary of a little teeny ball of fixed size, and the disk goes into the ball. So the boundary is on the boundary of the ball. So somehow, since you can relate intrinsic and extrinsic, then you can reduce down to this extrinsic question. What's the curvature at the origin? Assume that the disk passes the origin. Can it have big curvature at the origin? This is the disk, a ball centered at the origin radius delta. And can we have large second fundamental form at the origin? So we have constant mean curvature fixed here in this problem. So when you would like to do a rescaling argument, when you rescale, you get minimal surfaces. And since we're simply connected, right, since you're simply connected, you might believe you're going to get a simply connected blow-up surface. There's really something involved in showing that. But anyway, which comes up more in my next proof. So I'll skip it here. But rescaling arguments, a little bit of, for example, this dynamics theorem I mentioned before, allows you to see that you must get helicoidal type surfaces when you rescale. So it looks like a helicoid. And under a microscope, what you see is as the curvature gets bigger and bigger, it looks more and more like a helicoid. So a very important part of the proof here is actually the uniqueness result for minimal surfaces for the helicoid. We really use that it's a helicoid when you rescale. Okay, so then this is basically taken from, I guess, which paper is this? This is the paper. Koldemir have a series of 5 papers. I don't know if the last one's been accepted in the annals, but there were 4 that were in the annals. And see, which one is this? This is paper number 2. It has the, I'm sorry, the first paper, it's really kind of like the second paper, but it's number 1 in the series. Anyway, they have a nice result about extending minimal, extending minimal disks. They have some kind of property. You see a lot of sheeting, and you can somehow connect up in a topological way far from where this sheeting occurs, and some properties that hold. Basically, what they show is that you can extend a multigraph. So helicoid's got this multigraph. You can extend it, and so we managed to prove the same sort of thing for constant mean curvature disks. Okay, so again, there's an extension of these helicoidal graphs, and they extend out a definite distance toward the boundary of our ball of radius delta. And we get more and more sheets. Well, there's no space. There's no space for these sheets. They would, there's no space. How to say it? Constant mean curvature is kind of like this. And it's just no space to do that. So if you have too many sheets, then, excuse me. If you have too many sheets, yeah, there's just no space for it, and you get a contradiction. So anyway, that's what happens there. Okay, next. Okay, so that's how you. That's a sort of sketch of how you do this. It's kind of a long story, as you can see. There's probably a paper about this, and there's a paper about this, and then there's the compact case. It's kind of a long story. All right. Okay, so actually what I find is more interesting than that particular story is a radius estimate. Now, this is much more interesting from my point of view, but it says that if you take an embedded, for example, h equal to 1 disk in R3, there's a universal estimate for telling how far you are from the boundary. Again, this is kind of similar to some results about stable constant mean curvature disks. And there's some kind of flavor here that's related to being stable. Anyway, so there exists a universal constant. So if you take an h disk in R3, embedded h disk, then the radius of that disk is no more than t over h. Okay. So let me just give you the sketch. This sketch is kind of interesting. Again, to illuminate some of these new techniques. So first of all, by scaling, you can assume that everything is 1. So what would, if this were to fail, we're going to argue by contradiction. Suppose that we had a sequence of these disks, 1 disks, and points in these disks which were further and further away intrinsically from their boundary. Okay? Well, first thing that comes to mind is, remember we have curvature estimates away from the boundary. So just remove an epsilon boundary from all these disks to start out with, say the regular neighborhood of radius 1. That means we're talking about disks with there's a fixed estimate on the norm of the second fundamental form of all these disks. So it's natural to see what do they limit to by translating these points to the origin, and these disks start winding, getting further away. They sort of boundaries are somehow drifting away from where the point is at the origin. And in general, you don't get things that are embedded, but you can still prove that you essentially these. Well, anyway, you can get surfaces that are essentially embedded. It's like two spheres. Take two spheres, and you can translate them, and they touch. So you can have that kind of property. So they're somehow embedded. If you push them into the mean convex side, then you get embedded surfaces. So anyway, you get this sort of limit surface here. You can prove it's proper in R3 with constant mean curvature 1. So why is that going to be useful? Okay, so here's what comes up, one of these new results I think is probably very useful for our subject. And I say subject, I mean differential geometry. There's a very interesting sort of idea going on here. It's creating invariant sets, minimal invariant sets, some kind of dynamics. Anyway, there's something called the CMC dynamics theorem. It works in any dimension, and any codimension 1, but in homogeneous manifolds. Anyway, so what it allows you to do is you take a surface with bounded second fundamental form, and you translate it. Okay, you translate it, but you want these points to be going to infinity in the surface. Then, because of the bounded second fundamental form, and you can prove local area estimates, you get compactness, you get some kind of objects. And what you can prove is not really, there's really two theorems here. So there's something called the CMC dynamics theorem, which is kind of very general, but it's really the deeper theorems in the subject, in this particular subject, are what's called the minimal element theorems. So there's, you look at somehow the collection of all the limits. There turns out to be an operator. It's kind of like a diffeomorphism. You think of this set of surfaces as being like a manifold. And you look at orbits. You look at minimal invariant sets. And then you can always prove there exist minimal invariant sets. You look at elements in minimal invariant sets. Those are called minimal elements. And it turns out if you start out with a surface of genus 0, you always are going to get a Delaunay surface as a minimal element. So if you're more careful with your translations, you can get a Delaunay surface for a limit. You get this nice smooth convergence. The property of Delaunay is kind of like the property of a catenoid. It has non-zero flux. This is CMC flux. That's a homological invariant. So that means that the related disks over here had non-zero CMC flux. But that's a homology invariant. There's no one-dimensional homology on a disk. So we get a contradiction. So you can't make Delaunay surfaces because you start out with something simply connected. Okay, so that's the idea of that result. Okay, and then this is just kind of like just general. How do these things generalize to manifolds? So if you take any complete 3-manifold, you assume the sectional curvature is bounded, and you look at any H surface in there with positive mean curvature. Okay. Then you want to say, well, maybe I have curvature estimates again. And it turns out you do if you have positive injectivity radius. So the second fundamental form at M is positive. Wait, it's positive, bounded. Wait, second fundamental form is bounded. Positive. I'm thinking positive injectivity radius, that's word's not supposed to be there. It's bounded if and only if, when you lift the surface to the universal cover of N, it has positive injectivity radius. So it gives you a natural condition for understanding when you have bounded mean curvature, bounded second fundamental form, I'm sorry. And if you don't assume this estimate about sectional curvature, you have locally, on compact sets, you still have locally bounded second fundamental form or bounded second fundamental form. So you always get sort of a lamination structure on the closure of the surface, even if you don't make this assumption about the sectional curvature. You get better results in homogeneous 3-manifolds. So we can actually mimic a lot of things we know about R3 to any complete locally homogeneous 3-manifold even. It says homogeneous here, but in this, it's kind of a funny mixture here. So let's just keep the homogeneous. Suppose you have a complete embedded finite topology H surface in such a manifold. Then it always has positive injectivity radius. This is a property if it's minimal or if it's constant mean curvature, non-zero constant mean curvature. You always have this sort of nice property about the injectivity radius being positive. Then we can apply this theorem here. In the minimal case, we have a result that says that at least on compact sets, you have bounded second fundamental form, which means the closure is a minimal lamination. But if H is actually positive, then you have bounded second fundamental form. Okay? Now, if you assume that you're a finite topology and not necessarily a homogeneous three-manifold, but a quotient, then you no longer have this property about having positive injectivity radius, but you still have this property about having bounded second fundamental form when the mean curvature is positive. So if you're in for example, a compact homogeneous three-manifold, locally homogeneous three-manifold, then you again have the same sort of result about finite topology surfaces have bounded second fundamental form. Okay. And here's just to illustrate things can be quite different. These are infinite genus pictures. I just kind of threw them out because in actual applications, these are the ones people see in material sciences, like triply periodic or doubly periodic surfaces. And there are also lots of interesting things that one would like to do with our work to three-manifolds. So for example, if you're in a three-manifold, like a three-torus, like here, compact three-manifold, for example, take your favorite three-torus. Here we have a genus, looks like genus 3. So, this is bigger, but if you take a smaller lattice here, we have a genus 3 constant mean curvature 1 surface, say, in that three-manifold. If you bound the mean curvature away from 0 and above by some constant, and you bound the genus of the surface, it turns out in the same paper we did the curvature estimates, we proved that there are area estimates for all such surfaces. This is kind of similar to Choi and Shane's theorem. So, and again, you can generalize a lot of things into three-manifolds, but that's just an example of sort of where the subject can go. You can actually study compact constant mean curvature surfaces and understand their moduli space, the compactification of the moduli spaces, and lots of manifolds, like a three-torus. Okay, so again, where is this going? All right, so then we're kind of coming back to this removable singularities questions. They're really fundamental. Many years ago, partly motivated by a question Harold asked me, he asked, are there any foliations of R3 with leaves of constant mean curvature where the foliation is not parallel planes? Okay, we knew we can't have a minimal foliation other than parallel planes because leaves of a minimal foliation are area minimizing, they're stable, and therefore they're planes. So you can't do this with minimal, but maybe you can do it with non-zero constant mean curvature. So that actually motivated some of the earlier things I was talking about. Anyway, I proved you couldn't do it other than by parallel planes. But if you allow singularities, it turns out to be very interesting. There are lots of foliations of R3. For example, concentric spheres. Then you have a singularity at the origin. And this is a picture of an example of a CMC foliation. CMC means constant mean curvature foliation. That means I want the leaves of the foliation to have constant mean curvature. But I'm not saying I'm fixing the constant mean curvature. I'm letting it vary as I go from leaf to leaf. You can also prove some regularity property. Basically, this is, there's no regularity assumptions in this foliation property, not even Lipschitz. Just any foliation already has some regularity associated to it. All right, so if you have a CMC foliation of R3 minus a closed cannibal set, and here we have 2 points, then each leaf of the foliation is contained in a round sphere or plane. Okay, so let me just try to describe this. Now everybody can see things geometrically like me. So here, imagine you have concentric spheres, and then they kind of lose their being concentric. I mean, they're not concentric anymore. But the radius goes to infinity in finite time. I get a family of planes, and then I start shrinking the radius of those planes, like infinite of something finite, and I start getting spheres again, which can then converge down to this picture. So this is a foliation of R3 minus 2 points by planes and spheres. And you could ask, in what sense is this kind of universal? That's what this theorem says, somehow a universal. If you allow what's called weak foliations, weak CMC foliations, where you allow the leaves to touch on their non-mean convex side, you can, anyway, well, you can allow leaves to touch. Those are not very interesting if you have locally bounded second fundamental form. So if you assume you have locally bounded second fundamental form outside of a closed countable set, then in fact you can only have 0, 1, or 2 singularities for such a structure. Those are called weak CMC foliations. So here's the picture for 2. You could have 1, like concentric spheres, or you could have none, which would be parallel planes. So if you're willing to generalize, you actually get a much better result. You actually understand a wider class of foliations. And there you get very precise answers about the singular set. All right, so how do you prove such things? So notice the ingredients kind of over a couple different years here. So we're trying to prove this result. How do you prove it? Well, first you get this sort of nice result of trying to understand limit leaves of what's called an H lamination. So if you have a CMC foliation and you take a leaf in it and you take its closure, you get a bunch of leaves with the same mean curvature. It, together with some other ones, that's somehow a closed set, and that's what's called a H lamination. Again, this is a more general thing that you're allowed also to happen. But the crucial thing here is that the limit leaves of an H lamination are stable. This was used a lot by a number of different people. Coley Minicozy, Harold and I have used this a lot, but we only really used that the universal cover had this property, that the universal cover of a limit leaf of such a structure was stable. That's sufficient to get curvature estimates. It turns out for some subtle things, you really need this result. I'm not sure if you need it here, but anyway, that's one of the interesting ingredients. This works in any dimension. If you go dimension bigger than 3, you have to assume Lipschitz regularity. But anyway, so if you have of the lamination, we're always talking about codimension 1 properties. The other thing interesting is this local curvature estimates. So curvature estimates, if you have a foliation, you can talk about the norm of the second fundamental form of the leaves. You can think of it as an ambient function. At a given point, you look at the leaf going through that point, you look at the norm of the second fundamental form, and it turns out if you bound the absolute sectional curve of the 3 manifold, then you can bound the, what's S here? Sectional curvature. Right. If you bound the sectional curvature, then it turns out you have universal estimates for the norm of the second fundamental form of all CMC foliations and all of these manifolds. And that can be very useful. For example, in H2 cross R, Harold talked about this yesterday, it turns out the estimate that you get is the mean curvature is always less than or equal to 1/2. You can't have big mean curvature leaves. It's kind of like what happens in R3 when you had to have parallel planes. We're talking about no singularities. Anyway, there are lots of interesting ways you can use this. You can understand, for example, hyperbolic free space. Lots of interesting foliations. But they all have the property, their leaves have mean curvature less than or equal to 1 in that case. Okay, the other thing is that once you have curvature estimates and you allow yourself to have certain limits which have a very weak kind of singularities, you get compactness results, and that's very, very useful, these compactness results. So that comes from once you get the curvature estimates. And then you'd like to get removable singularity theorems for H laminations or foliations. So for example, suppose you have a 3 manifold, and in a neighborhood of a point, you have a CMC foliation. When can I extend across that point? I might touch myself, like think of 2 spheres touching a point. I mean, I'm allowing that when it's bounded second fundamental form. When can I extend to a structure with bounded second fundamental form across a singularity? It turns out it's sufficient to have bounded mean curvature in the neighborhood of the point. So which means that everything starts looking in 3 manifolds. Under scaling, looks like R3, and R3 we understand. So now with everything mimics what happens in R3. At somehow a possible singularity. If the mean curvature isn't bounded, then I rescale, I see spheres and planes in R3. I get like a foliation in R3. So anyway. All right, so here's I'm getting towards the end of my talk. So there's this general trying to question of what's the asymptotic behavior. Some important numbers here. Click here, I'm not doing the right thing. So this says that if you're given 2 numbers that are bigger than or equal to 0, there exist particular examples of properly embedded minimal annuli. They're sort of canonical examples. Think of these as canonical examples. EAB in R3. Compact boundary means like a circle. We're talking about annuli. So circle boundary, one curve boundaries. These could be ends of surfaces or something. Now, where are the A and B coming from? I've normalized these surfaces in some kind of way, and in particular in that normalization, they have a certain flux. So if you integrate the conormal and the boundary, I've rotated and everything so that I got some kind of flux A. In the x direction, I got some kind of flux B. In the third coordinate direction, I'll talk a little bit about the normalization of this in a minute. There's a notion of horizontal. People are familiar with Kolde-Minkowski theory. Multigraphs. So multigraphs in this picture for these examples are horizontal, like the helicoid. A vertical helicoid has horizontal multigraphs in it. So we're doing that sort of normalization. Helicoid also has a normalization by homothéty. The usual example of the helicoid has spacing between the sheets of pi. There's sort of two multigraphs, and spacing between from one multigraph to the other one is pi. I'm also normalizing these somehow in the same way. Okay, so what's the key steps, 6 steps to this? Well, first of all, complete embedded minimal annuli are proper. That we get from Kolde-Minkowski. They didn't do the compact when the boundary is there, but it's the same. It's the same. It's really nothing different. So they proved this in the case of completeness implies properness. So that gets us started. Then we sort of do some other things. We do a rigid motion of our general example. See, these are supposed to be describe the asymptotic behaviors of any example. So they exist, and they are giving us our asymptotic behaviors. So I'm trying to understand E here, okay? So, so if we're embedded, then we're properly embedded. And now I want to understand what's the asymptotic behavior. So I really want to restrict to a subend, because I don't care what happens near the boundary. Outside of a big compact set, what does it look like? Well, you can find a subend so that horizontal planes intersect the surface either far away from the boundary, so up or down. We intersect in one proper arc. Otherwise, we intersect the boundary, and we intersect in two points. We get 2 proper arcs. So anyway, that's one part of the proof. We wanted to get the conformal structure. This plays a very important role in understanding the helicoid. Helicoid is conformally C. The Gauss map is a meromorphic function with some properties at infinity. So we need to understand the conformal structure of the end. And it's standard. It's a punctured disk. It's the exterior of an open disk in the plane. So that's a conformal structure. Then the height differential in the wire stress representation has a particular form. Okay, so again, we're trying to normalize the example. So we then see that the height differential has this particular form, which if this was just 1 dz, we'd have the helicoid. So this perturbation that comes from the flux, the horizontal, the vertical, this third component here, that's the same number B. So there's some kind of perturbation there away from the usual helicoid. Notice that it decays as Z goes to infinity. This is becoming small. The meromorphic Gauss map, it has, again, something like the helicoid has. The helicoid would be E di Z, but we again have this sort of perturbation term, f of Z, where it extends meromorphically across infinity. So f infinity, in fact, is 0. We assume it's 0 at infinity. I'm going to say a little bit more about these in a second. And then you need to show that this end is actually asymptotic to our standard example, where we somehow have the same fluxes. So again, after doing these modifications in a homothéty, so some spacing is pi, then we have the same, we look at the same numbers that we get. And those numbers determine those forces determine which canonical example we have. All the canonical examples are different. So just a little bit more about these steps in this proof. So we have, as I said before, complete embedded minimal annuli in R3 are proper. That's Kolde-Minkowski. Again, there's a notion of having a horizontal multigraphs inside these annuli. And I should also say I'm only focusing on the infinite total curvature case, right? The finite total curvature cases are well understood. You got catenoids and planes, so everywhere everything's infinite total curvature. So in this case, we have we prove that that you can find this end that has this sort of nice intersection property, 1 curve or 2 proper arcs intersecting the boundary. And I don't know exactly about the order, but I know Joaquin Perez and I kind of figured this out a while back, and they had found probably independently found the same proof, and it follows rather easily from Kolde-Minkowski. I always wanted to know if they actually knew this, when they knew this, but it didn't mention it in the paper that we used. So anyway, so that's some kind of property you get. Remember I said that the E prime is conformally diffeomorphic to this, and it has this height differential. That follows essentially immediately from number 2 with some properties about harmonic functions on annular domains. We have a little paper where we just study harmonic functions on annular domains, and as a consequence of that, you get this information, immediate corollary of these properties about harmonic functions. Okay, meromorphic Gauss map is this. At least, how do we? What techniques do you hear? Basically, we just redo some of the things that I did with Harold and Rosenberg, but it's much easier. It's kind of much easier than what we did. But some of the things are just quotes out of, basically quotes out of the work I did with him. It's really nothing new here. Okay, so then how do you construct these examples? Well, we have the Weierstrass representation. So you can try to set up all these things up, and then you have to solve periods, so you have to get examples which have fluxes, and you have to prove embeddedness. So you have to be able to find the right F here, so that you can solve the period problems, and also, then you also have to prove that these canonical examples are embedded. So there's just a basic theorem. When you have a representation like this, we prove it's always embedded on some sub-end. So the canonical examples have this representation, so they're embedded. And the last step is prove that the fluxes determine the asymptotic behavior. So then you have to prove that you're asymptotic to this. So lots of calculations, geometric interpretation of the analytic data. This would, unfortunately, Harold and I never tried to interpret what was really going on when we were trying to prove the uniqueness of the helicoid. We just went through and calculated and applied theorems and stuff like that. But it's actually worthwhile to think a little bit about what's happening. And then everything becomes much more geometric and easy, instead of lots of horrible estimates, which is the standard way undergraduate would do, kind of analyze this thing. It's not the right way to go, in my opinion. But anyway, so we did kind of try to get nice proof. All right, this is kind of pointless. I'm going to come back to this. All this nonsense here is trying to describe things with words. Unfortunately, I didn't make a great picture. I did this. I was already very late to catch my airplane to come to Rio. I did this very fast. I tried to do another picture on the blackboard here. So let me just explain, how does the flux determine the geometry of EAB? Now that's interesting. How do these numbers A and B, what's going on there? Remember, A is the x1, sort of the x1 flux. B is set up to be the vertical flux. And so in this picture, what you end up having is you go to plus infinity, or if you translate down, or translate the surface down, then I convert to a helicoid. If I translate up, I converge to a helicoid, but they aren't the same helicoid. So somehow there's a helicoid as I go vertically up, and there's a helicoid as I go vertically down, and they have different axes. The axis is where the Gauss map is vertical. Okay? And of course, somewhere in here we have the boundary of the surface. All right, so think of the x1 axis as coming out straight out of the blackboard. Then the spacing between the axes of these helicoids is this vertical flux. Not the vertical, the x1 flux right here. That's the spacing between the axes of the helicoid. And you could say, well, what is the number B? It turns out there's some, if you look at outside of some big cylinder, you have two multigraphs. So think of a big cylinder that has the axes of the helicoids, these two helicoid ends in it. Then you get this sort of trace curves. You get two trace curves on the cylinder. And they pretty much look like helices, but there's a logarithmic term that somehow they sort of drift up logarithmically as you travel on them. Interesting, if you go out horizontally, if you fix at theta, of course there's small theta here. If you go out horizontally, it turns out you get this for uniform kind of growth as long as b is non-zero. You get like a log r growth on the going straight out. But on the given range, you get these sort of logarithmic growth that has to do with the b. Okay. In other words, you fix r and let theta vary. All right. So that's all the rest of that there was just talking about that, trying to describe it in words. And the picture is just so much better. Okay. So I'm going to end my talk with one more sort of discussion. In my opinion, probably there's a bunch of these Calabi-Yau problems. They're just really interesting questions. And they come up in lots of different places. For example, questions that are very important in homogeneous three manifolds, like nil. We'd like to understand a lot of things related to Calabi-Yau and nil. So for example, are finite topology surfaces of minimal or constant mean curvature, are they always proper in nil? Probably so. Anyway, there's lots of interesting questions. So this is just new vocabulary. Suppose you take a domain, I'm going to think of a compact domain in a three manifold, okay. So suppose that D is suppose you have a domain like an open set in a three manifold, and suppose that for some non-compact surface with boundary, compact boundary here, you don't have any complete properly immersions of that surface into the domain with bounded mean curvature. Then I will say that's a Calabi-Yau domain for that surface. So we're just you could think of your favorite mean curvature and make it constant, but you could generalize the question. Do certain domains admit complete, proper immersions with bounded mean curvature? And it turns out we can get some obstructions. Now, one way to get domains is to take like a ball on a three manifold and remove the boundary. Okay? So suppose you have a compact, smooth three manifold with boundary, non-empty boundary. And my W here, which is like D here, that's going to be the interior. I'm sorry, it's not quite the D yet. So I take the interior of this manifold. I can find a collection of closed curves, or we can find a collection of closed curves, a proper collection, and remove them from W. Okay? That's going to be our domain D. And then for we prove that that domain has the property that it's a Calabi-Yau domain for any surface M with compact boundary and at least one annular end. In other words, annuli will not live in such a manifold in a complete proper way with bounded mean curvature. So nice pictures, and I won't talk about that because I think it's about finished. But anyway, it's very explicit how you construct these collection of curves. They kind of link and do kind of confusing, interesting things. But in a compact set, you only see a finite number of them. Okay, so that's I think that's probably time for me.
Questions, please? Okay, thank you very much.
Okay.